Alright, so AP Calculus AB, the second derivative test. This is the second video on this. The first one just went basically kind of what the mechanics of that look like. This, hopefully, we're going to apply it a little bit here, so let's use this test. It says let f be a function such that f prime at c, this is crucial that we read this carefully because this is the critical value that we're looking for here, and the second derivative exists on an open interval containing c. And here are the three conditions. If f double prime at c, this c being this c, is greater than 0, then f has a relative minimum at c f of c. Secondly, if f double prime at c, remember this c is the one that we got from the first derivative, critical value here, right? So critical value here. Then we have a relative max at c f of c. And in the case that we have f double prime at c is equal to 0, we cannot draw any automatic conclusions. So let's try this a little bit. Let's try to apply this test here. So let's start with the function. Our function is f of x is equal to negative 3x to the fifth power plus 5x to the third power. So what we're going to do first is just something simple, which is to take the first derivative. From here, remember, we're going to find our critical values. So I'm assuming that you know how to differentiate, so let's just differentiate this thing together. Plus 15x squared, right? Wow, it's 15x squared is our first derivative, right? Take this first derivative, set it equal to 0, and I guess the way I would do this, I would break this out. I would just rewrite f prime at x. I'd factor out the 15x, so I'd take out 15x. This should be to the fourth. Take out 15x squared, and I'd multiply that by 1 times negative x squared. That gets us, if you look at that, it gets us all this stuff back, doesn't it? So if you look at this and solve each one of these for 0, this one equals 0 when 0 is here. And this one equals 0 when x is equal to 1 or negative 1, right? So we have those three critical values, don't we? So these are our critical values right here. So let's keep track of that a little bit. So here are our critical values. Right? Critical values. Those are those c values that we were talking about before. So then we're just going to set up this table a little bit and take a look at it. We're going to say, well, what are the points here? Right? We have points here. And what are the points? Well, we have the point negative 1, 2, right? If you take, remember, if we go back to the other page, we get this point right here. We get negative 1, f of negative 1 is what it says here. And we get that point, and when we put negative 1 into the first function, we get negative 2 back, right? And then we want the sign of f double prime at x there. So f double prime at negative 1, well, is greater than 0, right? So we know, so our conclusion here is that we have a minimum. If you're a little bit lost here, go back in the video for a second and write down those rules that we were just going, because that's all I'm doing. I'm assessing at critical values, and we got our critical values here. So the first one was negative 1. The next one I'll do is 1, if you don't mind. So, sorry. So the next point is 1 something, so it's 1 f of 1, and f of 1 happens to be 2, so 2. And then we're going to assess f double prime, the second derivative, when x is 1, and it happens to be less than 0, which means, right, that we have, oh, I should have put an r here, relative minimum here, we get a relative max, don't we? Right, these are the conclusions that we should be drawing. And then here at 0, 0, right, we have f double prime at 0 equals 0, right? The test fails here, so we can't draw a conclusion. So the test fails. That doesn't mean we stop. The test fails means we have to go on and find this a different way. So what we're going to do is, because the test did fail at 0, 0, we have to use the first derivative test, and we observe that f is increasing from left to right. To the right of x equals 0, so 0, 0 is neither a relative minimum nor a relative maximum, even though the graph has a horizontal tangent line at this point. So we can actually, if you want to know what this thing looks like, it's kind of a weird looking thing here, but it looks like this. And we know our function is chordic, so it's going to have some kind of weird kind of W-ish shape, and it looks like this. Our function looks like this. our function is continuous. I just draw this because I think it's pretty. So it looks kind of parabolic here, and then it comes up to here, right? And then what happens is it kind of dips for a second, and then its concavity changes, and it looks like that, and then back down like this. That's a horrible looking picture. But you can see now, hopefully, that this point right here, right, we said this is a minimum, and it's this point right here. This point right here is the point -1, -2. The point 0, 0 is neither a relative max nor a relative min, is it? And then here's our relative max here, which is the point 1, 2. Relative max is some kind of, relative max and min are sometimes called local maxes and mins, and it's where the direction of the function changes direction. So on the interval from here to here, we do have a real minimum here, and on the interval from here to say here, we have a relative maximum there. So, okay, that's my first attempt to try to show you this rule. So hopefully it worked well. I'm looking forward to you taking good notes and asking questions. Please subscribe.